Good afternoon, everyone. I'm Philippe Chartier. I am currently at Inria Center at the University of Rennes in the west of France, and more precisely in the math department in a team that is devoted to something that they call effective geometry and algebra. Okay, and there's a part of this team that is involved in cryptography. Okay, prior to that, I was with Ravel Technologies, for which I worked something like a bit more than 3 years. And we are still, of course, collaborating. Okay. I'm very grateful to the FET meetups organizers and to Ben Curtis in particular for the invitation. And the work I'm going to present now was already presented at AsiaCrypt 2024 in December. So I apologize to those who were there in Kolkata, if any, of course. This work was done in collaboration with three colleagues, sorry, four including me. Two colleagues from Ravel Technologies, so Florian Mea and Michel Koskas, and a third colleague, Mohamed Lemou, from CNRS Irma, again at the University of Rennes. And this work was done where we were all four of us were at Ravel Technology, so it was prepared during this time. So the title, as been said, the title of my talk is homomorphic sign evaluation with a residue number system representation of integers. And something that is not mentioned in the title is that we mean large integers. So we'll come back to that. Okay, so boom. Okay, sorry. So a few words. I'm not going to stay very long on this talk, on this slide, sorry, because you are likely already very familiar with the concepts and the history of FET, of course. So I won't delve into the too many generalities, but well, I will just mention a few facts about the evolution of FET and TFET in particular, because this is what I'm going to talk about. So as you all know, the work of Greg Gentry in 2009, which has triggered a lot of research, and it's only recently that some years ago already, but a number of startups have emerged that are now developing FET libraries, and Ravel Technology is one of them, which specifically focuses on privacy-preserving targeted advertising on one hand, and secure data analytics on the other hand. So why is the reason why we chose TFET, the TFET scheme in particular? The choice is to use this scheme is primarily motivated by two reasons. Well, first of all, as everyone knows, again, this TFET is based on lattices, and so this offers post-quantum security. And the other aspect that was very attractive is that TFET offers one of the fastest bootstrapping processes. If you compare it to other schemes, at least in terms of latency, of course, when it comes to amortized bootstrapping, the situation is a little bit different, but for the latency, it's clearly a must. Okay. Sorry. Okay, so the technique has been described in several key papers that I've just mentioned here very quickly again. So the first one, so it's two different names for two different variants of the same thing. So the first paper was a paper by Leo Duca and Daniele Misianzo, and it introduced a very fast bootstrapping at that time, even with bootstrapping in less than a second for the FET scheme. And then this work was further optimized by four people, so Ilaria Cilotti, Nicola Gama, Maria Georgieva, and Malika Izabashen, and was published in AsiaCrypt in 2016. And they reduced significantly the time of the bootstrapping. And the third paper is a sort of elaboration of this with a lot more details, but the ideas are contained already in the second one. Okay, so well, here comes the very familiar commutative diagram. So you know it by heart, of course, everybody here. But since we focus on in very large numbers, large integers, and by large here I mean 32 bits or 44 bits integers. And well, we will have to represent numbers in a certain way. I will come back to that, but the main operations that we want to include in our FHE implementation are the addition, of course, as usual, the multiplication as usual, and in comparison. So why do we insist on the comparison? Well, it has to do with, let's say, for example, well, there are several situations, of course, where you have to compare numbers, but a prominent one is certainly when you deal with databases, where you have to sort lists of numbers, and that means comparing numbers 2 by 2. And what is a comparison? If you compare A and B, well, you essentially form the difference of B minus A, and then you determine the sign of that. This is how you compare numbers. So we want to do something. We want to get some implementation of FHE implementation where you have these three operations. So if you have plain text A1 and A2, you want to be able to say, for instance, evaluate A1 plus A1 times A2 less or equal to A2 with the output, which is a Boolean, equal to plus or equal to 1 or 0, according to whether this inequality is satisfied or not. And you want to do you want to be able to do the same thing, the very same thing, but on the ciphers. So if you encrypt first A1 and A2 to get C1 and C2, well, you want to be able to perform the very same relation, the very same computation, C1 plus C1 times C2 less or equal to C2. And of course, you're going to get something which will be an encryption, an encrypted value, an encrypted Boolean in that case, which should be just the encryption of the plain text result. Okay, so this is what we aim at in this talk. And well, I'm not mentioning all other possible homomorphic functions that you might wish to incorporate in a FHE implementation. This is something different. But I will concentrate now on this comparison operation, and especially on the sign, which lies at the core of any comparison. Okay, so first, a few slides on how we represent numbers and how we encrypt numbers, large numbers. So, of course, there are several ways to do that, and I'm not going to discuss them, the merits of each. But say they could be you could represent a number, an integer, by its binary decomposition. But another possibility is to use the Chinese Remainder Theorem. Okay. But first of all, we will use an algebraic object that is very simple, that was used already by many others before us, which is the discretized torus. So this discretized torus, it is just a structure which is inherited from the ring ZP with the addition and the multiplication, and so it has also a ring structure, as can be seen very easily. So if you enumerate all the elements in this set, let's say TP, for a p greater or equal to 3, you will get something. So here is always going to be, p is going to be odd in the rest of the talk. Okay, so it's an odd number. So I represent these numbers by minus p minus 1 divided by 2 up to p minus 1 divided by 2. And the privileged representative will always be the element modulo 1 that lies in the interval minus 1/2 plus 1/2. So essentially, this is just TP is 1 over p ZP. And it's very easy to see that it inherits the structure, well, first of the continuous torus for as far as the addition is concerned. So if you want to add two elements of the torus TP, the discretized TP torus, then you just add them in T, and nothing special. But for the multiplication, of course, you have to do something a little bit different, because you can't multiply two numbers in the torus, which is not a ring. This is a Z module. So what you can do is you can uplift one of the two operands. So say X, for example, you multiply it by P, and you get an integer that you can now multiply by the other element here, y, with the modular product, okay? And this all makes sense. So you completely inherit the ring structure here. That's very easy. But I don't want to insist too much on that. This is just what we're going to use for the rest of the talk. Well, how do we encode numbers? Well, there are several steps in that. Well, what we do is, so we consider a large integer, p, and we assume that this is a product of kappa, pi, which are going to be assumed to be co-prime numbers. So for each pair, I different from j, pi is going to be prime, co-prime with pj, okay? And so as before, of course, this discretized torus, T capital P, is made of the enumeration of the numbers minus p minus 1 divided by 2p and up to p minus 1 divided by 2p. And these can be represented in an unambiguous manner for the Chinese remainder theorem. So it's going to have a coordinate for each I, okay, corresponding to the modulo pi. So how do we do that? This is very easy again. You just to get the moduli and the representative in the in TPI of the modulus, sorry, mu I. How do you do that? You multiply p, you multiply mu by p, of course, and you take the modulo pi and divide by pi, or you multiply mu by p, divide by pi, and take the modulo 1, which is obviously equivalent. Okay, so in this way you can associate to each mu in T capital P, you can associate kappa numbers, which are elements of the Cartesian product of TP1 times TP2 times etc. times TP kappa. Okay. Okay, so the Chinese remainder theorem states that this is a bijection. This is an isomorphism, to be more precise. And it has, of course, an inverse. And this inverse is very helpful here because it allows to reconstruct, at least up to some modulo, the original message mu. So if mu is in TP, you can construct its moduli, take its moduli in each ring, TP1 times TP2, etc. But you can also do the reverse. So if you have the moduli mu1, mu kappa, you can also reconstruct mu with the help of the Bezout numbers. So all of you know what the Bezout numbers are. They are obtained from the Bezout identity, which you have to write for each pair, pi and capital P over pi. Okay, so if you do that, you get Bezout numbers, ui and vi, and you can use these vi's to reconstruct the mu, modulo 1. Okay, so, well, I think this is not really needed, but let me emphasize that one of the main interests of considering this residual number system representation is that when you have to perform an operation like the addition or the multiplication, this can be done on each ring individually. So you can add mu I and nu I for each I, and this can be done in parallel, or you can do the same, of course, for the multiplication operation. Well, so this is very convenient, and this is very nice. You don't have to take care of carries or whatever. It's very simple. Okay, so once you've got these moduli, you have to encrypt them, and we do encrypt them separately. So we use LWE encryption scheme, the same for all of them, all the moduli. And we do that so in the usual way. So we assume that we have determined some cryptographic parameters so that the encryption is secure, okay? And so that means that we form the pair of A and B in the torus with n+1 components by first sampling A1, AN, the vectors of torus values with uniformly, and then we multiply this by the secret key S, which can be chosen with elements in any set S. There's no restriction at that point. So we form the scalar product of A by S. We add the element of the torus mu. We add some noise, which is here a Gaussian noise with the appropriate parameter standard deviation. And we get this B, okay, this scalar B, which we add to get the LWE encryption. This is completely standard. So we do that we're going to do that for each individual component, each individual modulus, okay? So if you want to decrypt, of course, you cannot do that for any element of the torus. It has to be discretized. You have to know in advance where you look for, and then you project on the discrete torus TP. So you have to give TP when you decrypt. You give, of course, pair A and B, and if you know the key S, you take B minus AS, which is called the phase, and you project it on the torus to the closest representative in the torus TP, and you get the decryption of C. Okay, so that's very, very standard. So if I want to sum up all the process, the encryption process, here's how I can do that. First I start from a mu in TP. It's a message, okay? It's a large message in the sense that capital P has many elements, okay? Capital P elements. So first we compute the residues. So capital P times mu modulo P1, capital P times mu modulo P kappa, okay? We encode them by dividing by the corresponding modulus. So this becomes capital P times mu divided by P1 modulo 1 up to capital P times mu divided by P kappa modulo 1. And then we encrypt individually each of these residues, okay? So we get we get kappa LWE encryptions of mu1, mu2, mu kappa. If you want now to decrypt, well, you just reverse the arrows and you get up in the diagram. And so you first decrypt each element individually. So you get now these residues in the tori. And then once you've got the residues in the tori, you can uplift them to the element of the rings ZP1 up to ZP kappa, and then by taking the linear combination with the Bazoo numbers, you of course recover the message. Okay, nothing new in that. This is just a representation that we have adopted here for its convenience. Okay. Now let me come to the main point of this talk. Which is the computation of the sign. Okay, so first of all, let's say a few words about how we define the sign. Okay, it's not completely immediate, although this is very obvious, but we have to decide how we represent the sign. So we decide that we consider the representative of an element mu in the torus. So I call it mu, and we take the representative mu prime, which lies in the interval -1/2 +1/2, and we are going to decide, as expected, I would say that the sign of mu is the sign of mu prime in -1/2 1/2. Okay, so -1 on in the interval -1/2 0, 0 if it's 0, and 1 in the interval 0 1/2. Okay, so now the main thing is the following. We want to recover an encryption of the sign of the reconstructed value that we could get from the residues mu1, mu kappa. But of course, we don't get the residues. We don't have the residues mu1, mu k. We just have encryption of those. We have encryptions CI of the LW, so encryption CI of the mu I. Okay, and we want still, without decrypting, as usual, we want still to be able to compute the sign and an encryption of the sign. Okay, so how do we do that? Well, let me first make a sort of a preliminary remark. I mean, as I said, this Cartesian product of tori is very convenient when you want to add or multiply numbers. It's also relatively convenient when you want to compare two numbers, because the identity, if to compare, sorry, if you want to decide whether two numbers are equal, because if for two numbers to be equal, well, all residues should be equal. They should coincide in each ring. Okay, so that's also something which is not too difficult to understand. But now, if you want to decide what the sign is from just the residues, you cannot get the sign of the reconstructed value by just looking at the signs of the moduli. Why is that? Well, this is just an example. You take T15, so T15 is the Cartesian product of T3 by T5, okay? And as we have decided, so we look at the representatives of two numbers, 2/15 and 7/15, and they have now we look at the moduli in the torus, in the tori T3 times T5, so we get -1/3, 2/5 for the first one, sorry, and 1/3 and 2/5 for the second one. So although 2/15 and 7/15 have the same sign, they are both positive. Well, the signs of the moduli are quite different. It's a pair made of -1 and 1 for the first one, and 1 and 1 for the second one. So it's clear that we cannot obtain the sign of mu in T capital P just from the signs of the components. We have somehow or at least to some extent, try to recompute, to reconstruct for the inverse phi minus 1, the value of mu. Well, we know that it's not possible per se, but we need to get some approximation of that. In order to evaluate the sign, that's what we need to do. Okay, so as I said, we're going to try to recompute this this message mu in T capital P. Well, we could try. A first attempt is to try to get an encryption of this mu, and since everything is linear here, see, I mean, this LWE scheme is very nice because it's linear. So if we form the phase of each element, so bi minus ai, we would recover mu I plus an error ei. Okay, this is just by definition of the scheme LW itself. And if we now compute this linear combination, which lies at the top of this slide, so the sum from I to kappa of the Bezout numbers vi times ai bi, we get an encryption of the reconstructed value mu. That's clear by linearity again. But the problem is that the error has also been obtained by a linear combination of the individual errors ei. So E is the sum from 1 to kappa of the Bezout numbers vi times ei. And this might get far too large for a correct decryption in T capital P. Well, this is of course completely expected, because precisely the thing we wanted to do at the very first was to represent a large number with smaller ones, because it was not possible with reasonable parameters to represent that number directly. So it's not surprising that we cannot recover a correct decryption. However, we can use that to some extent. Let me. This is what I'm going to show now. So first, if we look at these errors, I mean, if you want to decrypt each mu I correctly, then this error should be less or equal to 1/2 pi. This is obvious, because this is just half of the space that you have between two numbers. Okay, two numbers in TPI. And so, of course, if you assume that all these mu I can be correctly decrypted, you get an error, a bound of the global error E, which is huge. Okay, you just get something like kappa over 4, where kappa is the number of rings that you have to use in your RNS representation. And this is, as I said, far too large. So if you take an example, say 7, 11, 13, 15, 17, 19, 23, and if you want to ensure that each mu I can be decrypted with a very high probability, higher than 1 minus 10 to the minus 10, even in that case, the probability of a failed decryption is very high. So to the point that it's completely meaningless. Okay. So here is the main, well, the next slides are going to describe the main trick that we're going to use here. So we first define an approximate function g epsilon on the torus in the following way. And let's keep in mind that what we're going to use is not mu, but a noisy value of mu. That's we're going to work with noisy values. Okay, so if we look at a mu value and say if we are in one of these red zones, because mu is not known exactly, but with some error, it is not possible to assert with complete confidence that the sign is 0, 1, or -1 when you are in the red zone. But when you are in the green zones, and if you assume that the errors are not too large, here is something like an error smaller than epsilon over 2, then you can assert with great confidence, well, complete confidence, that this is either 1 or -1. So the 0 here in this function, it doesn't mean that the sign is 0. It means that you don't know what the sign is, which is rather different. But in the green zones, you know that the sign is going to be 1 or -1. So let's see what happens. Okay, so we assume that we have a noisy value mu til of mu with some error e, which is bounded by epsilon over 2, and epsilon is smaller than 1 over 8. Well, to make things work, we need something like an assumption like that. Okay, so we start from a scaling factor. It will become clear in a moment that this is a scaling factor, p bar, which is a not integer. That's fundamental. Otherwise, it doesn't work. So p bar is in between 3 and capital P, and we assume that epsilon is small enough as compared to 1 over 2 p bar plus 1. So from this noisy value of mu, which I call here mu til, okay, we are interested in the value of the function g epsilon of mu til. Well, if you look at what happens, if this g epsilon of mu til is 1, then you know for sure that the sign of mu is 1. Why is that? Because if g epsilon of mu til is 1, it means that you are in the green zone on the right of the interval, -1/2 plus 1/2. So you are in between epsilon over 2, 1/2 minus epsilon over 2. And since the error e here is less than epsilon over 2, even when you add this error, you know that mu is going to remain in the interval 0, 1/2. So the sign is +1. And you can say something completely similar on the left. Okay. Now, something more that I need to explain is the situation where g epsilon of mu til is 0. So that means you are in one of these 3 red zones. In that case, you cannot say anything about the sign of mu. That's the problem. And so this is the main difficulty. But now, because of the choice of p bar and epsilon, you can assert that p bar times mu, so the scale value of mu by p bar and mu, they have the same sign, the very same sign. Okay, and of course, we're going to use this a lot. So why is that? So see, if j epsilon of mu til is 0, okay, that means you are in one of the red zones. So suppose, for example, you are in the red zone in the middle, and suppose in addition that mu is positive. That means you are actually in the interval 0 epsilon. And in that case, it's very easy to check that p bar times mu is actually in the interval 0, 1/2 minus epsilon. So that means that the scale value p bar mu is in the 2 zones, the green zone plus the red zone in the middle here. And if you start somewhere on the right, so in the red zone on the right, something similar happens. So if you start in this interval 1/2 minus epsilon 1/2, then p bar times mu is going to stay in the interval epsilon 1/2. Okay, so that means the signs of mu and p bar mu are the same. Okay, so now the idea is to consider a sequence of rescale values. So of course, they are going to be obtained from the noisy values mu til I. So how do you do that? Normally, if you look at mu till 0, this is just the sorry. So if you look at mu till 0, this is just the reconstructed value. Okay, nothing special. But now so this is vi modulo pi times mu till I. And now we multiply this by a scaling factor, which is here p bar to the r, okay? And what we get in this way is an approximation of p bar to the r times mu plus an error. And the very important thing to notice here is that this error is bounded by the same quantity for all values of r. This is because p bar times vi, although it grows, only its modulo matters. Okay, so we take its modulo pi, and so this does not grow. Okay, so now if we look at the sequence of values g epsilon of mu till k, and if we assume that this remains 0 for some time up to r, okay, well, we know from the previous result that the sign of all these scale values, so p bar k times mu, is the same as the sign of mu. And now suppose that at the next step, so for k equal to r plus 1, suppose that you don't get 0 any longer, but you get a sign, so you get +1 or -1. Then you can assert for sure that the sign of mu is +1 or -1. So this sequence is very useful, but this is not the end of the story, because there is something that needs to be understood. Of course, you cannot monitor the sequence, because although we are now discussing the situation of the algorithm for clear text values, at the end of the day, we're going to use ciphertext. So we never know when this g epsilon is going to change from 0 to 1. All these values are encrypted, of course. So what we need to know is that there exists a value for which actually this happens. So the sequence of values k equal to 0, 1, up to r, etc., it's going to end at some point with a value 0, 1, or -1. So three possibilities. Either this sequence is always 0 and remains 0, or it starts with 0 and it becomes 1 or -1 at some point. Okay, then we know that we can decide what the sign is. But what we need to know is whether this sequence is finally changed, we're going to get a sign. And this is true because if we start from the red zone here, okay, we start from the red zone, and with a mu which is in 0 epsilon, say, well, the scale values p to the r times mu, they grow. This is a growing sequence, and at some and we know that two consecutive, if the first one is in the interval 0 times epsilon, the next iterate is in the interval 0, 1/2 minus epsilon. So, and we know that we're going to get out of this red zone because it grows, the sequence grows. So the first time we get out of this zone, we actually end up in the green zone where the sign can be determined. So we never jump. What happens is that we never jump from a red zone to a red zone. We first go through a green zone. So that ensures that the sign is going to be determined at some point. So what happens, of course, for this sequence here on the right of the interval, this is also true if you start from the red zone on the right. At some point, you leave this zone to enter the green one. And if you start on the left of the interval -1/2 and 1/2, this is also similar. So starting in the red zone minus epsilon 0, after some iterations, you're going to end up in the green zone. And if you start from the red zone completely on the left of the interval, so between -1/2 and -1/2 plus epsilon, you're also going to go through this green zone where you can determine the sign. Okay, so you know that there is some value at which this will happen. Well, the last thing that we need to ensure is the value of this r. Can it be very large, or can we estimate it? And is it is it finite? Okay, well, it is finite because we know that this grows, this sequence of values is growing, and because of the choice of the parameters p bar and epsilon, we know that it is bounded. So we know that r star is bounded by some value r max that we can actually estimate with the formula that is given here. So 1 plus the entire part of this logarithm p in basis p bar of capital P divided by p bar plus 1. And so we know that this sequence is going to end up in one of these green zones where you can determine the sign. Okay, well, if you have followed until now, which I very much hope, you should be a little bit puzzled by the fact that we still don't know where this jump is going to occur. So when do we actually jump from a red zone to a green zone? You don't know, once again, because everything is encrypted. So you can't really estimate this turning point. You have to do something different. And here is what we have suggested to do. So we take a weighted sum. So we take the values g epsilon over these consecutive iterates till r. So we take these, we compute this mu till r, as I said, so by the scaling factor p to the r, p bar to the r, sorry. And we multiply this by a weight, and this by a sequence of decreasing weights. Okay, that's the important thing. This sequence is so 2 to the r max minus r is a decreasing sequence. So you start, say, with, if you start with 1 or minus 1 for g epsilon, this is going to get a very large weight. Okay, the highest weight actually. And if you start with 0, this does not count in the sum until you reach an iterate for which it becomes 1 or minus 1, and then the weight is going to be the largest one of the remaining, the weight that you attribute to this value of the epsilon, the first one to be non-zero, is going to be the dominant one in the sum. So at the end of the day, all we have to do is to compute this sum, okay, this weighted sum, and then evaluate its sign. And again, this can be done with the function g epsilon, okay, which is the approximate sign function. Okay, so let me just show you what happens in practice, kind of practice. So if you start from a mu till r, which is approximately mu, so mu plus some error, in the interval, if this is in mu epsilon for mu, well, g epsilon is first 0, okay, because this is not large enough. You are in one of these red zones. So g epsilon is 0. It remains 0 for a while. And in the sum, capital S here, so this sum was just what I had here at the top of the slide here. So this sum that I call here S is 0 and remains 0 until you reach this R star value. And then this is the point where you have switched from the interval 0 epsilon to the interval epsilon 1/2 minus epsilon. And we know this is a green zone where you can assert that the sign is 1. Now, this value 1 is going to be multiplied by capital M. So if you look at the bottom here, M is 2 to the R max minus R star. So this is the largest so far weight, okay? And so the next iterates, they can take values in the set -1, 0, and 1. So whatever they are, these values, they're not going to change the sign of the sum. And this is because the weights are decreasing, okay? So even if this is, let's say, -1 at the next iterate, you get M minus 1 minus M over 2, which is M over 2. And the next step again, if it's still -1, you get M minus M over 2 minus M over 4, etc. And since this sequence is limited by R max, at the end of the day, even if all the remaining signs, all the remaining values of d epsilon are -1, this remains positive. Okay, this is due to the choice, of course, of the weights in the sequence. Okay, this is something I'm not going to describe very much. This is just an example. So you take these values, 7, 11, 13, 17, 19, 23, 25, 27, and so that you can get a lot, well, you can get 32 bits, sorry. And say you choose P bar, this is just an example, equal to 13. You can compute R max, turns out to be equal to 8. Then if you compute the Bezout coefficients, and you look at now at these famous growth factor, so that these Bezout numbers time the scaling factor P to the R, but modulo Pi. Of course, if you look at the variance of E, you can sum all the variance, and then in that case, you've got a growth factor. And this is just to show you that this growth factor is not as bad as you could expect because of this moduli. So if you examine carefully what happens, this growth factor is not too large. It's not as large as you might expect, actually. So this was just a small example. So this of course I have presented here the algorithm only for clear values. So this was the choice of mine because you can get all the ideas from the algorithm for the clear values. All you have to do once you've done that is to, of course, you have to implement these sums here. So you have to compute the mu tilde. This is not difficult. You have to compute d epsilon. This is a bootstrap, okay, because it's a nonlinear operation that you need to do on the reconstructed value mu tilde. And so this is a bootstrap. And then well, actually, you can combine the bootstrap and the multiplication by the weight. And then you sum all this. And at the end of the day, you get another bootstrap to get the final sign. Okay, this is the way it is done for ciphertext. Okay, so just I will conclude my talk with a few numbers to just show you some of the average times that we get for 32 and 44 bits numbers, integers. And so there are four lines, so two lines with 32 digits and 2 lines with 44 digits. And this P fail, let me just say what it is. This P fail is the probability of that the sign is incorrect. So because you actually have to perform several at least 2 bootstraps, okay, then there is a probability that actually what you get at the end is incorrect, and we actually estimate this probability. So of course this is something that matters a lot in practice. So and here I have also given so the sign here is in column 5. Okay, so you get these numbers in milliseconds, and just for the purpose of comparison, you get also the numbers for a multiplication. So this is something like well, between 2 to 3 and 6 times the time of multiplication itself. Well, of course, the addition is very is harmless. Well, it's not very significant here. Anyway, this concludes my talk, and I would like to thank you for your attention. If you have any question, I'm ready to answer them, of course. Thank you very much.